Okay, so now the contact force we'll be looking at is tension. Tension is the force that is generated in a rope or a string or a cable or any similar object when it is pulled upon. So here we have two characters pulling on the string, or rope I should say, and there is a tension then in this rope. Of course this tension is acting on the person here, and over here it's acting on the person's hand here, and those forces are equal and opposite. If we were to take a microscopic view of this rope, and let's say we could see all the molecules, then those molecules would be in bonds, and we could treat those bonds as if there were a lot of little springs. So imagine then that this rope is made up of millions of little springs that are very, very, very stiff, in the sense that when they pull on this rope, it doesn't stretch much at all. Now, in actual fact, this does stretch, but normally it doesn't stretch so much that you would see it. However, even though we could look at this rope as being made up of millions of tiny little springs, we still use a separate term for the force here, and we call it tension. And the symbol we'll normally use is capital T with a little arrow on top. So that's all we'll say for this force for right now. Okay, so now we look at the normal force. Students often find this force a bit difficult to understand. Let's take this example here. We have a box on a table. Why doesn't this box fall? The earth is pulling on this box. This box has weight. Let's represent the situation here with what is called a free body diagram. So I just use a particle to represent this box, and we know that there is the pull of the earth acting on it. So this is the weight. That is the pull that the earth is exerting on this box. The nice thing about free body diagrams is that they allow us to focus on exactly where our attention needs to be placed. So if this is the only force acting on this object should accelerate downward. It should pick up speed moving downward. Obviously, this doesn't happen. So that means in this particular case, there must be some other force acting in the opposite direction that exactly counterbalances this one. So I think I drew this a bit too big, more or less like that. And this force now is the force that the table is exerting upward on this box. So we'll call that the normal force. Sometimes we use small n, sometimes we use capital N. Likewise, sometimes I'll use capital W and sometimes small w. Now, why do students find this difficult? It's because we often associate force with something that is alive. So we think of human beings exerting force, or an animal exerting a force, like a horse pulling something. Students find it very hard to think that a table that is not alive, it's an inanimate object, that somehow this table is exerting a force. The mere word exert is probably the source of the problem. When we think of exertions, we think of someone doing something and maybe getting tired. You exert yourself. But that's not what we mean here. We simply mean that this table is applying a force to this object. But maybe that doesn't help either, because how can it be applying something if it's not alive? So one way to think of this is to imagine this table as maybe a bed of springs. And of course, if you have a bed of springs, when you place an object on it, those springs will be compressed. And then what you'd experience is the spring force acting on that object. So one way to look at this normal force is to think of it as the result of all those little spring forces acting upward. In a case like this, the springs would be very, very stiff, so you would not see much of a compression here. The normal force doesn't have to act vertically. For example, here we see a box on a ramp, and the ramp is exerting a force on this box. What we can say that is true always for the normal force is that this force is always at 90 degrees. It is always perpendicular to the surface that is exerting the force. So notice here, the normal force is perpendicular to the table. Here, the normal force is again perpendicular to the surface. Now we'll talk about friction shortly. So what we have here are the three forces acting on this object. There is a normal force from the surface of the table. There is the weight due to the earth's pulling down on the box. And there is friction along the surface. So we'll discuss friction shortly. Here is another example. We have someone pressing a book against a wall. So this hand is exerting a force to the right, of course, the wall is also exerting a force on this book. And so we could draw that force this way. And so now we have the normal force acting here. Later on we'll see that there is also, later on we'll look at a problem that involves a situation like this, and we'll see that, well, the forces, you also have friction acting up, and there's a weight acting down. And of course there is the force exerted by a hand on the book, which acts to the right. So notice these two forces will be equal in magnitude, but they are not the same force. This is the force that the hand exerts on the book. This is the force that the wall exerts on the book. So we don't have a symbol for, or a name for every force that we'll encounter. So when they don't fall in one of these categories here, we simply use the symbol F. So if I have a lot of forces, I might call them F1, F2, F3. So then this would be friction, and this would be the weight. Okay, so now we turn our attention to friction. To help us get an understanding of this force, we'll turn to our good friends at the University of Colorado at Boulder. So again, great applets here. Make a donation if you can. The applets they provide are very useful. Anyway, so getting back to our situation here. Here we have a man standing up beside a crate, and this is a wooden floor, so it's a bit rough. And he's going to apply a force. So let's apply this force. Let's say he applies 23 newtons. Notice the crate doesn't move. Let's make that 80 newtons, 90 newtons. The force that he applies, which is the orange force, does not change the crate's state of motion. Why? Because as he applies that force, the floor also applies a force, and that force is the force of friction. So let's, instead of dragging the slide, just type a number in here, like say 200. So now notice we have a force of 200 being applied. So that is the force that this man is exerting upon this crate. But the floor also exerts friction, a frictional force on the crate. So notice what you have here is the free body diagram drawn on top of the crate. This force is actually at the surfaces in contact. Note also we have these other forces here. This is the force of gravity. So these people like use Fg, I would use W for weight. And this is the normal force. Again, they use Fn where I would just use N. So this is the applied force, and that is the frictional force. So let's make this 300. Notice the crate still doesn't move. So this friction is called static friction, and static friction prevents relative motion between two surfaces in contact. So note the word there that you want to pay attention to is prevent. Static friction prevents relative motion between surfaces in contact. Of course, for it to prevent this relative motion, there needs to be some tendency for this motion. And of course, this applied force is responsible for this tendency. If there were no applied force, there would be no friction. So let's bring this back down to 0, and note there is no friction. So static friction can only exist if there is some tendency for motion. So let's make this 350. Notice it still doesn't slide. So the static friction grows as it needs to in order to prevent that relative motion. Let's make it 400, and notice the friction has grown. What we're going to find, however, is that this static friction can't grow indefinitely. There will come a point where it can grow no more. And at that point, if this force increases anymore, then we'll have an unbalanced force, because the applied force will now be greater than the opposing friction. And as a result, this crate will accelerate to the right. Now, once there is relative motion between the crate and this floor, the frictional force will drop significantly. Once there is relative motion between these surfaces, the friction is called kinetic friction. And kinetic friction opposes the relative motion between surfaces in contact. Note now I say oppose, not prevent. It's just opposing it. So let's see what happens if I increase the force a bit. Now it's 411, then 423. Notice the frictional force, the static friction is growing to meet it. And somewhere around here, we should find that it can't grow anymore. So notice what happened there. Let's reset this. If I apply this force somewhere around 450, we see what's happening there. Let's do this again. Note something very important. Once it's moving, when I release it, when this man stops pushing the crate, the friction will continue to oppose the motion, and as a result, the crate will slow down and eventually come to a halt. So let's do this again. Notice, so we know already around 500 it's going to go. And then when I release it, see, it comes to a halt. Once more. See, and then it comes to a halt. So let's discuss the theoretical aspects of this a bit more. So let's get the notation down. For static friction, we'll simply use small f with an s, and of course our little r. Remember, this is a force, so it's a vector. And for kinetic friction, it's a small f again with a little k, and again we have our little r on top there. So how do we calculate these frictions? Let's suppose we have a surface and we have an object on this surface, and this is being subject to some pull. So I'll just write some F there like that. So what other forces act on this? Well, there is the pull of the earth, so there is the weight, and there is a normal reaction. Horizontally, we only have one force, so this should accelerate to the right. However, if we have friction acting, and this friction is equal to this force, then it won't be accelerating. Let's suppose we started from rest and we have this force applied to it and it's still at rest. Well, obviously then this will be static friction. So this static friction will go from a value of 0 until some maximum value. After that, this static friction won't be able to grow anymore, and then this thing will begin to accelerate to the right. What is the maximum value this static friction can achieve? Well, we have a simple little formula for that, and I'll just say that the magnitude of the maximum static friction is going to be equal to something we call the coefficient of static friction times the normal reaction. So this coefficient of static friction, for right now, let's just look at this as expressing the degree of roughness. The rougher the surface is, the greater will be this coefficient of static friction. Of course, we can see here that this coefficient is equal to the ratio of the maximum static friction and the normal force. A more intuitive way of interpreting this is to say that the maximum static friction depends on how much these two surfaces press against each other. So notice that the maximum friction does not depend on the weight. It just so happens in this situation the magnitudes of the weight and the normal reaction will be the same. But remember that this friction, the maximum value of this friction, is not a function of the weight, but rather a function of the normal. How much does this surface press up against this one? Now it comes to kinetic friction. Well, we don't talk about a maximum value now. We just say the magnitude of the kinetic friction is just simply going to be equal to some coefficient of kinetic friction times the normal reaction. Now we're going to find that mu k is less than mu s. So everybody probably has experiences at some point in time. Let's suppose you have a crate that you're trying to drag across the floor or push across the floor. So you push on it, and then it starts to slide. And you find that once it starts to slide, it's not so hard to push anymore. That's because the coefficient of kinetic friction is less than the coefficient of static friction. So if this were moving, then this would be a k here. So I won't redraw this. Not moving relative to the surface, it's static friction. Moving relative to the surface, kinetic friction.